So we really need an intelligent approach to this problem. What I have done is I have looked at this A matrix, this constraint matrix, and really found a very strong structure in this matrix. We can see what we have plotted here are the non-zeros in the A matrix. The blue areas are non-zero coefficients, and the remainder of that space is all zeros. So you can see we have a very sparse A matrix. The top half of this A matrix are the network constraints, the general flow constraints. The bottom half are those side constraints. That top line of constraint coefficients is the capacity constraints we mentioned earlier, and the lower chunk is the opposing move constraints. And what I have found is that if we branch, if you look at this highlighted set of columns there in the middle of the matrix, if I branch on those first, that dramatically improves the speed and quality of our solution. That is really the way to tackle these. So my solution methodology for these problems is to first turn off all of the CPLEX defaults. And I don't have time to go into all of that now, but I have to tell you also that the default heuristics in CPLEX are counterproductive. They will really slow this solution down dreadfully. So we want to turn them all off. We want to disable all of those defaults. Secondly, we want to branch on those departure arcs. We want to branch on those highlighted columns in the A matrix. We want to branch on those first. And finally, the ordering of the A matrix is very important. We want to structure and order the A matrix formulations so that we see that nice structure as it's sent to CPLEX. That has an impact on the way CPLEX responds to the problem. And if we do all of this, there's a dramatic performance improvement. On average, over a set of 24 problems, I see before making this change, I have a 1.96% average MIP gap. After I make these changes, I have a 0.74% MIP gap. And those results are not even really as dramatic as the reality. The averaging is, there's a few bad actors that drive those averages up. And let me show you an example. Here is an example, a typical example of one of my runs, one of my problem runs, solution runs. And here on the right, the yellow and the pink. The yellow is what is called the upper bound, the best node of the solution as it's progressing over time. Time is on the horizontal axis in seconds, and the pink is the current best integer feasible solution as the solution is progressing. And the difference between those is called the gap, and if you're not familiar with that, that is called the MIP gap, and that is the gap between your current best known bound for the problem and the current best feasible solution. The objective is to close that. The program is done, the solution is found when you have closed that gap, and you now know that your current feasible solution is also the best optimal, the best bound solution. And you can see it takes a number of minutes to acquire that solution under the default settings of CPLEX. Now on the left, the light blue and the dark blue, that is the best bound and the best integer solution sequence when I have implemented my changes, when I have implemented my branching strategy. And you can see that there is no competition. The methodology, the instructions I give to CPLEX allow it to solve the problem before the default scenario has even registered its first result. It's a huge, and this is very typical of most of my problems. So in most cases, I believe in actually about 18 out of the 24 results, I obtain optimal solution in less than 300 seconds. Implementation, I'm on Windows XP. All of these solutions are being generated on my little Dell laptop here because again, it's not brute force that is going to solve these problems. It really is an intelligent approach is what will solve these problems. And so it doesn't really pay for me to invest in a much more powerful computer, because doubling my computing power isn't going to solve these exponential problems. I have a database, custom-written database in FileMaker that I use to store my problem scenarios. That database can then transmit that problem scenario to AMPL, which configures the sets and the rows and the columns, and then sends the problem to CPLEX. CPLEX solves the problem, and then the solution is retrieved back into my database, where I can view the solution and manage the results. Here is a picture of the database. Here's the control center for my database. In the upper left, I can pick track networks and I can pick trains to run on the network. In the upper right, I can give various instructions to CPLEX about how I might want it to solve the problem. And then the bottom, I have an actual graph picture of the train schedule solution. And on the right, lower right, is the statistics of the solution. That solution is called a string-line train diagram, and here is a more specific picture of one. This is the model output. So the diagram has geography on the vertical axis and time on the horizontal axis, and this is a typical railroad scheduling diagram. And the line that's going up and then coming back down again, that is a round-trip train, and then the line that is gently sloping down from the upper left is a one-way train, and everywhere that the train stops and waits is a horizontal line segment. And there are two places on that diagram where the trains have what's called a meet, where they meet at a siding and pass each other. So we wanted to get back to this business of pricing on the network. We want to price new and diverse services. So the way I accomplish this with my model is first I establish a homogeneous host flow, and I label this arbitrarily 60 miles an hour. It's meant to imply a homogeneous base flow of, say, coal trains or general freight or this kind of thing. And I want to fill the network to capacity with this base flow. So I have got modeled here a set of trains that have completely filled the network. There is no more room on this network for additional trains, and I establish the objective value for this maximum flow at 39 and change. And then I force on top of this flow another train, and this other train will be one of these fast trains or a passenger train or one of these non-conforming trains that I want to value on the network. I force it onto the network, but I do not give it an objective value. I force it on with the constraints, but it has a zero objective function, and that way, once I have forced it onto the network, I measure the new objective of the system, and the difference in the objective is the net cost of forcing that train onto the railroad. Here are the results for a series of problem scenarios, series of forced train scenarios. What I have done is I have my base flow, and then I tried two different train speeds forced onto this flow. There's an 80 mile per hour train speed and a 120 mile per hour train speed, and they are essentially, we have a 1/3 increase in speed and a doubling of speed to look at. And then I've looked at both adding a one-way trip or a round-trip forced flow. So that's what the trains added column is. And then I tried two different subtle changes in the network structure, the way in which the sidings are set up. And then the results are in these objective deltas here. We have three dispatch scenarios. The first one is none. That implies that whatever train that I have forced onto the network must get to its destination, but it has no priority in dispatching, so it is always submissive, it is always secondary to whatever traffic it meets. The middle column is the equal priority. That implies there's a roughly equal valuing of train delay at passing locations. And then there's the absolute dispatch priority. And the absolute dispatch priority means that whatever train I force onto the network is absolutely higher priority than whatever traffic it meets. So the forced train always has priority dispatch at every meeting location. And if I look at this data, there are a couple of really interesting results. First of all, across the board, faster trains are better. So if I'm going to force a train onto the network, anything I can do to